Alright, welcome back to section 1.9, Proportionality and Power Functions. This is our last section for chapter 1. So we are first going to discuss proportionality. So this is a common functional relationship. Alright, so we stumble upon proportionality quite frequently. Alright, so this is when one quantity is proportional to another quantity. Alright, so for example, I'm going to zoom in a little bit more. There we go. For example, if we were to look at the price of apples, alright, say it is $1.40 per pound. In other words, the price that you would pay depends on the number of pounds that you buy. So it depends on how many pounds of apples you buy. Alright, so if we take the price and we say it's a function of the weight of apples, it would be $1.40 times the number of pounds of apples that you would buy. So this would be our price function or our cost function. Alright, where the cost, the total cost, maybe I'll say cost instead of price. The total cost is proportional to the weight of the apples. Alright, we also have different kinds of proportionality. So in this case, a little bit more space. In this case, the price increases. Again, I'm going to say cost instead of price. The cost increases as the weight increases. Alright, so both quantities are increasing. This is called, this is called directly proportional. Directly proportional. Alright, and that brings us to our definition. So we say that some quantity y is directly proportional to another quantity x if there is a non-zero constant k, so that's our non-zero constant, such that we have this equation, y is equal to k times x. Alright, where k is called our constant of proportionality. Alright? So I mentioned earlier that we have different kinds of proportionality. So that was directly proportional. And we also have inversely proportional. So we also have inversely proportional. Alright, so this is when one quantity is proportional to the reciprocal of another quantity. All right, so let's do an example. So for example, the time it takes to go some distance is inversely proportional to the speed at which you are going. All right, so what does this mean? Well, in other words, one quantity is increasing while the other quantity is decreasing. So in our example here about the time and the speed, the faster you go, so if speed is increasing, then the less time it's going to take you to get where you need to go. So we have time would be decreasing. All right, so if we were talking about a 50-mile trip, we would have the equation, our speed, which we like to call v, is equal to 50 times 1 over t. And this is our inversely proportional to time. So this is our reciprocal of time. All right, so now we'll do our first problem. We have George buying a cart full of watermelons. All right, and the cost of his grocery haul is proportional, there we go, proportional to the number of melons that he buys. What is the constant of proportionality if the trip costs a total of $79.80 and George left the store with 20 melons? Interpret the constant of proportionality and determine the units. All right, so let's get some important information here. We've got proportional going on. We've got a total of $79.80, and we're leaving the store with 20 watermelons. So earlier we had the cost of apples, right? So we had the cost is equal to, again, we're using our equation for proportionality. So our cost is proportional to, so this is our constant of proportionality, the number of watermelons. I'm going to use W for watermelons. All right, so our cost is proportional to the number of watermelons that he buys. This is our equation. All right, so what are we asked to find? We're asked to find the constant of proportionality. All right, we're given that the total cost is $79.80 and the number of watermelons is 20. So we have $79.80 is equal to K times 20. And we need to find the constant of proportionality. So we'll divide both sides by 20. Get 79.80 over 20 is equal to our constant of proportionality, which gives us K is equal to 3.99. All right, so then we're asked to interpret the constant of proportionality in this situation. So we found K, and now we're asked to interpret it. Well, and the units are going to help us interpret this here. So let's think of what we've got going on in units for cost. So the cost is dollars, right? And W is the number of watermelons. That's our unit over here, is a watermelon. Okay, so we've got K is equal to cost divided by number of watermelons. So our units for K is going to be dollars per. Sometimes we read this bar, this division symbol, we read it as per watermelons. These are our units for K. Is going to be dollar per watermelon, or dollars per watermelon. All right, so if we're interpreting our constant of proportionality, $3.99 is going to be the cost, or I will say price, the price of one watermelon. That's our interpretation of our constant of proportionality in this case. All right, so let's do another example. Your weight on the moon is proportional to your weight on Earth with a constant of proportionality of 0.16 or is 0.1655. If Jacob weighs 30 pounds on the moon, how much does he weigh on Earth? All right, so we have our weight on the moon. I'm going to say this is capital W sub m. That's our weight on the moon. Okay, it is proportional. So it is proportional to your weight on Earth. I'm going to say capital W sub e. All right, so I just took that first sentence and turned it into an equation. We have the weight of the moon. It's proportional to the weight on Earth, not your weight of the moon, your weight on the moon. Okay, we are told that our constant of proportionality is 0.1655. We're also told that Jacob weighs 30 pounds on the moon. So his weight on the moon is equal to 30 pounds. We want to know how much does he weigh on Earth. So we're going to plug these two values into our equation here. We have weight on the moon is 30 pounds is equal to our constant of proportionality, 0.1655, times weight on the Earth. So again, we need to divide both sides by our constant of proportionality. So we'll get 30 over 0.1655 is equal to weight on the Earth. And we can go ahead and plug this into a calculator, and we can find that Jacob weighs 229 pounds and 6 ounces on Earth. All right, and that's our final answer for that problem. All right, so for example 3, we have Jen and Kyle moving across the country, and they need help packing up a moving truck. If it takes 6 people a total of 4 hours to pack up the truck, how long would it take 10 people, assuming everybody works the same? All right, so we'll highlight a few important things. We have 6 people and 4 hours. All right, and then it's asking us how long would it take 10 people, assuming everybody works the same. So the first thing we need to figure out is what kind of proportionality are we dealing with here? So let's think about it. If it takes 6 people 4 hours, say we add 4 more people to that, so now we're talking 10 people, and they all work the same. They're all working very hard, helping out their friend. So we would assume it would take them less time. So if the number of people increases, I'll write this out. So if the number of people increases, and in turn the number of hours, I'll say the number of hours the number of hours it takes them to pack decreases, right? We're assuming it's going to go faster. If I could spell, good golly, decreases. All right, so if the number of people increases while the number of hours it takes is decreasing, we have inverse proportionality, right? So our formula is going to look a little different than the last two examples. We're going to have the number of people, all right, we said is inversely proportional to the time. So again, we still have k as our proportionality constant, but now it's proportional to the reciprocal of time. Okay, so we're told that we started with 6 people, and that, or, you know, they did a trial run with 6 people, something like that, and it took 4 hours. So t is equal to 4 hours. So if we plug this into our equation, we get 6 is equal to k times 1/4. Well, we want to solve for k to find our constant of proportionality. So we'll get k is equal to 6 times 4, which is 24. Okay, so now we've found our constant of proportionality. So our equation looks like p is equal to 24, 1 over t. So the question is actually asking, how long would it take 10 people to do this same work, to load the truck? So now p is equal to 10. We already know our proportionality constant is 24, so we're just looking to solve for t. So we'll go ahead and plug 10 in for p is equal to 24 times 1 over t. So we'll go ahead and multiply both sides by t to get 10t is equal to 24. We're trying to get t by himself, so we'll divide both sides by 10. Get t is equal to 24 over 10, which gives us 2.4 hours. So, assuming all of their friends work at the same pace, if they have 10 friends helping them out, then it would only take almost about 2.5 hours instead of 4 hours. All right. So, power functions. All right. Our first definition in this section, we say that capital Q of x is a power function of x if Q of x is proportional, that's how this is related over here, proportional to a constant power of x. Alright, so what does this look like? It looks like Q of x is equal to our proportionality constant times x raised to some power. Alright, where k is still the constant of proportionality. And p is the power. Alright, so example 4 asks us to determine whether each of the following is a power function. If it is, we're going to state the values of the constant of proportionality and the power, and we're going to write it in this proper form of y is equal to kx to the power p. Alright, so let's look at A. We have y is equal to 1 over x to the 5th. Well, let's just rewrite this a few ways to see if we can get it to look like our highlighted equation. Alright, I'm going to go ahead and claim that this is a power function. And we're going to find that out in just a second. So we can rewrite this as 1 times 1 over x to the 5th, right? Okay. And then we can rewrite this again as 1 times x to the negative 5th power. Do we agree with this? We can raise our x to the 5th into our numerator just by making our power negative. All right, so yes, this is a power function. This is looking more like our highlighted equation where k is equal to 1 and our exponent is negative 5. Our power is negative 5. All right, let's do it again. So part B gives us y is equal to 14 times the 7th root of x. All right, how can we rewrite the 7th root of x? So I'm going to leave this 14 here. So writing any kind of root is the same thing as raising x to a fractional exponent. So x to the 1 over 7 is the same thing as the 7th root. All right, so again, yes, this is a power function where k is equal to 14 and p is the fraction 1 over 7. All right, let's look at C. We have y is equal to 4 times 3 to the x. Now, there's definitely a power happening here, right? There is something raised to something. There is an exponent. However, our definition of a power function said it must be a constant power of x. So it must be x raised to a constant number. Number. There we go. All right, that being said, this is not a power function. Okay, let's keep going. Part E, we have 2 times x all raised to the 4th power. All right, let's see if, again, we can rewrite this. Well, because we have multiplication between the 2 and the x, we're allowed to distribute this exponent, okay? I'll just make a quick note over here. If we had 2 plus x raised to the 4th power, we could not do that. All right, so only when there's multiplication happening inside our parentheses, okay? What can we distribute our power? All right, so this is now 2 to the 4th times x to the 4th, right? So it doesn't matter what 2 to the 4th is. It's some large number, right? Or larger number. However, it is a constant. So, yes, this is a power function where our constant of proportionality is 2 to the 4th and our power is 4. For part E, this one had me for a little bit. I'm just going to tell you right now that this is not a power function. However, it is a combination of power functions, and we're going to get back to this in just a little bit, okay? And our last part, part F, we have y is equal to 2 over 6 times the square root of x. We'll go ahead and rewrite this. So we have 2 over 6 times 1 over the square root of x. That 2/6 simplifies to 1/3, and we can take this x times 1 over square root of x is just x to the 1/2. Remember those fractional exponents. And we can move it around one more time to get 1/3 times x to the negative 1/2. We bring it up back in our numerator, right? We just have to make the exponent negative. So, yes, this is a power function with k is equal to 1/3, and our power is negative 1/2. Alright, so I promised we'd circle back to e here in a minute, and that is in our section of quadratic functions and polynomials. Alright, so here, power functions can be added together. And this will form, and this forms polynomials. Alright, now polynomials look like y is equal to p of x, and that's equal to, this is going to look scary for a second, and then we're going to deconstruct it, okay? So we have a sub n times x raised to the n plus a sub n minus 1 times x to the n minus 1 plus plus a sub 1 x to the 1 plus a sub 0. Technically x to the 0, but anything raised to the 0 is 1, right? So we typically don't write x to the 0. Alright, so I said we were going to deconstruct this. N is some non-negative number. Alright, and n is called the degree of the polynomial. The degree of the polynomial. Alright, n is the largest exponent in a polynomial. Okay, so as we see, our next exponent is n minus 1, then the next one would be n minus 2, and here we get all the way down to 1 and then 0. So n is always going to be our largest power. Okay, I will make a little note that the largest exponent might not be in the front. So I'm saying that the largest exponent might not always be in the front, and that's just because addition is commutative, right? So you can move things around a little bit. So you just have to look through the whole polynomial to find the largest number. That's all I'm trying to say there. Alright, we'll see an example here in a moment. So then we have a sub n. So that's all of these guys, right? A sub n minus 1, a sub 1. These are all just numbers, alright? They're just coefficients. I'm going to say a sub n's are coefficients. Alright, they're just numbers. So a sub n, the very first one, is called the leading coefficient. The leading coefficient, alright, which is part of the leading term, which is the whole deal, a sub n times x to the n. Alright, again, these might not always be in the front just because sometimes they get to move around. Alright, but we typically write everything in the highest exponent all the way down to the lowest exponent order. So this is why we call a sub n the leading coefficient. So a sub n is the one that is always multiplied by the highest degree of the polynomial. Alright, and then we have a special word for polynomials of degree 2. So if n is equal to 2, I'll also say if a polynomial has degree 2, then it is called a quadratic. And basically, because we have a special name for it, it means we're going to see a lot of it. All right? So instead of saying a polynomial of degree 2 all the time, we'll just say a quadratic. All right? And it's going to look like p of x is equal to ax squared plus bx plus c. And of course, our leading coefficient cannot be 0, or else we wouldn't have a quadratic, right? This whole term would go to 0, and then we would only have x to the first power, and we just have a degree 1 polynomial. All right, so this type of equation describes a parabola. All right, so one of these guys on a graph. That's a parabola. All right. It might open up, it might open down, depending on the leading coefficient. All right. The parabola will open, there we go, up, I was thinking of up there, if the leading coefficient is positive. I'll underline that whole thing. All right. Otherwise, the parabola will open down. I'll just be super specific and say if the leading coefficients is negative. All right, so example 5, this is going to be our last one, but it's a doozy. All right, got a lot of parts to it, but it's going to help break this down for us. So we're going to suppose a farmer has 20 feet of fencing, and she wants to enclose a section of her ground that borders on a river. The area enclosed will be a rectangle, but only 3 sides will be enclosed by the fence, as the other side will just be the river. By the following steps, we're going to find the maximum area that a farmer can enclose. All right, so part A asks us to draw a picture of the situation, and we're going to label W and L for the width and the length. All right, so here is our river over here. Okay, and we're trying to enclose some area in fencing that borders the river in a rectangle, like so. And then we are to label width and length. So this is the width, this is also the width, and I'm going to use curly L, okay, for our length. So we're done with part A. Moving on. Part B. What is the area enclosed by the region? Well, we have a rectangle, so our area is just our length times our width, right? Part C. Assuming the farmer uses all 20 feet of available fencing, write an equation that gives the perimeter of the enclosed space. All right, so there's kind of 2 steps in here. First, we're going to write an equation that gives the perimeter. All right, so the perimeter of a rectangle is normally 2 times the width plus 2 times the length, right? Now, why would I say normally? What's different about our problem? Well, our problem is only going to have one length side, right? Because there's going to be no fence against the river. So instead of saying plus 2L, it's just going to be plus 1L, or just plus L. Alright, so that's our equation for the perimeter. And we're assuming that all 20 feet of available fencing is going to be used. So that's going to say we assume our whole perimeter is going to add up to 20 feet. So if we want to plug this into our equation for our perimeter, we're going to get 20 is equal to 2 times the width plus the length. And that's all we have for part C. Alright, part D asks us to solve for one of the variables in part C. It specifically says one of the variables will be easier to solve for than the other. And honestly, both of them are pretty simple, right? If we take a look at it, it doesn't seem too challenging. But which one might be a little bit simpler? If we have 20 is equal to 2 times W plus L, whenever we have to solve for something, we need to get it by itself, right? Well, L is already pretty close to being by itself. All we have to do is move that 2W out of the way, right? So let's go ahead and solve for L. So we're just going to move 2W over by subtracting it from both sides. So we'll get 20 minus 2 times W is equal to L. Alright, we're done with part D. Part E. We need to plug our result in from part D to our result into part B. This should create a quadratic equation. And we just learned that our quadratic equation, this is a polynomial of degree 2, right? We just have a special name for it. Alright, so part B was our area. I'm going to say from B, we have area is equal to length times width. And from D, we have that length is equal to 20 minus 2W. So we're supposed to plug our answer from part D into our answer from part B. So now we have the area is equal to the length, but the length is 20 minus 2W times W, where W is still our width, right? Let's go ahead and distribute this W in, so we'll get 20W minus 2W squared. Alright, we have a degree 2 polynomial. So this means we have a quadratic. Remember, it's the largest number in the exponent. Here we only have 1 in the exponent, but it's just understood that it's there, right? Oops, the W is still there. Now remember when I said leading coefficients might not always be in the front? Well, this is what I mean. It's our second term here, right? But that's okay. We can just move it to the front. Do you agree that I just wrote the same two things just in a different way? Alright, so now it is truly the first term and the leading term in our quadratic. Alright, and that's all I meant by make sure you're looking through the whole formula before you pick the exponent that is the degree of the equation. Alright. So we did indeed create a quadratic equation. Good. Now, part F asks us to graph the parabola. Remember, we determined quadratic formulas gave us a parabola. Alright. And then it asks us some things about the parabola. We'll get to that in a second. So, we're going to go ahead and graph. For graphing purposes, I'm going to say y is equal to negative 2x squared plus 20x. And we'll see if it can graph this one for us. There we go. Alright, so sure enough, That looks like a parabola, doesn't it? Let's go ahead and insert this on the page. All right, let's move this down a little bit more. So we have a parabola. Is the vertex of this parabola a minimum or a maximum? So this is our vertex of our downwards facing parabola. So if it's a minimum, it means it's the smallest number that the parabola ever attains. If it's a maximum, it means it's the largest number that the parabola ever attains. So here, our vertex is a maximum. All right, because it is the highest value that our parabola attains. All right, the last part of this equation, or this question, asks, how could you know without looking at the graph? So, if we just looked at our equation, A is equal to negative 2w squared plus 20w, how would we know if the vertex was a max or a min? Well, our leading coefficient is negative 2, so it is negative, meaning our parabola opens downwards. Our parabola opens downwards. Downwards. Okay, the vertex of a downwards facing parabola, my goodness, I cannot spell today, a downwards facing parabola is always going to be the max. All right. Likewise, the vertex of an upwards facing parabola is always going to be the min. All right. So that's part F, and part G is our last part. It asks us to either use our calculators to find the minimum. So the last part is part G. Either use your calculator to find the max or find the vertex algebraically. What is the maximum area the farmer can enclose? And what values of length and width should she use to attain the maximum? So I'm just going to draw our quick graph over here one more time. It looked something like this with our vertex here. And the vertex of a parabola is usually labeled as HK. I'll move that a little bit closer, where H is our x value and K is our y value. All right, or in this case, our W value and area value. All right. So our formula for H, again, you could use a calculator for this. I'm just going to go ahead and do it algebraically because it's not too many steps. But we have a formula for H, where it's negative B over 2 times A. And where do B and A come from? Well, those come from our coefficients of our quadratic equation. So we had A is equal to negative 2w squared plus 20. And remember, we said a quadratic equation looked like ax squared plus bx plus c. So, with the squared variable is a. So a is negative 2. B is 20. And we don't have any just plain number added or subtracted from our polynomial, so c is 0. All right, so we come over here to find h, which is our w value, right? And we have negative b, so that's negative 20, over 2 times a, which is negative 2. So we get h is negative 20 divided by negative 4, so we get h is 5. All right, so what is the maximum area that the farmer can enclose? Well, h we said was our w value. So if we take a is equal to negative 2 times w squared plus 20, oops, I don't need to know that, 20w, and we go ahead and plug in our max value in for our width over here. We have the area. It's a function of w, right? So I'm going to say of 5 is equal to negative 2, 5 squared. That looks like 25 squared, so there we go. Plus 20 times 5. So our area is equal to negative 2 times 25 plus 20 times 5 is 100. Well, negative 2 times 25 is negative 50 plus 100. Area is going to be 50 feet squared. All right, 50 feet squared is our area. So what is the maximum area the farmer can enclose? I'm going to say 50 square feet is the max area the farmer can enclose. Okay, so what values of length and width is she going to have to use to attain this maximum? Well, we already determined the width, all right, and that was our h and k values. So our width was 5 feet. So what is our length value? Well, earlier, back in part D, from part D, we have that the length is equal to 20 minus 2 times w. So if w has to be 5, then L has to be 20 minus 2 times 5. Well, 2 times 5 is 10, so 20 minus 10, length, must be 10 feet. All right, so we have now found the maximum. This is 5 and 50, right? Our width and maximum area. And she has to use a length of 10 and a width of 5 feet to attain this maximum. And that is the end of example 5. So don't forget to take the last comprehension quiz and then get ready for the exam. And I will see you all in chapter 2.